Good morning and welcome to the 2017 AP Chemistry FRQ number 3 walkthrough. Number 3 starts by saying at high temperatures N2 gas and O2 gas can react to produce nitrogen monoxide and O gas as represented by the equation above, which is up here in green. A says write the equilibrium expression for the, or Kp, for the forward reaction. So whenever it's asking for K, you're always going to be, K is always products over reactants. So in this case, we're talking about pressure. So it's going to be the pressure of your products over the pressure of your reactants. My products are on the right side of the reaction. We're talking forward. So it's going to be the right side of the reaction. So it's going to be P, my NO gas. And I'm going to square it because there's a 2 out front. Squared. Divide by the pressure of my N2 gas times the pressure of my O2 gas. And there you have it. That's all it's asking for. Part B, and then it continues on. It says, a student injects N2 gas and O2 gas into a previously evacuated rigid vessel and raises the temperature of the vessel to 2,000 degrees Celsius. I'm going to underline that. That might be important. At this temperature, the initial partial pressures of N2 and O2 are 6.01 atmospheres and 1.61 atmospheres, respectively. The system is allowed to reach equilibrium. The partial pressure of NO at equilibrium is 0.122 atmospheres. Calculate Kp. Okay. And then I drew an ice table. Let's talk about why. First things first, it says initial and equilibrium allowed to reach. That's initial, change, equilibrium. And I'm trying to find Kp, which means that I need the values of the pressures to solve for Kp. So let's go ahead and fill in my initial values. It says it injects N2 and O2. There's no mention of NO, so that's got to be 0. The initial pressure, partial pressures of N2 and O2 are 6.01 and 1.61 respectively. So 6.01 goes with the N2. 6.01. And the O2 is 1.61. My change is based on my reaction here. So for every one of these I lose and every one of these I lose, I gain 2. So this is going to be minus x plus 2x. So at equilibrium, this is 6.01 minus x. This is 1.61 minus x. But this, they tell me, is 0.122, which means I can solve for x. In other words, 0 plus 2x, or 2x, equals 0.122, which tells me that x equals 0.061. Oh. Double check my sig figs. 1, 2, 3 sig figs there. 1, 2, 3 sig figs here. Now that I have x, I can go ahead and plug it back in for each of these values. So this is no longer 6.01 minus x. This is 6.01 minus 0.061, or 5.95. This is not 1.61 minus x. This is 1.61 minus 0.0610, or proper number of sig figs, 1.55. That's still 0.122. Now that you have these values, you can go ahead and take them over here, plug them in. So this will equal pressure over your NO is 0.122. Don't forget to square it. Pressure of your N2 is 5.95. Pressure of my O2 is 1.55. Which gives me an answer for B of 0.00161. And that's it. K doesn't have a unit. So your answer to B is 0.00161. And if we want to logic check ourselves really quick, we had a lot of N2, a lot of O2, and we got very little, relatively speaking, NO out of it, which means that the reactants are favored in this particular reaction, which means we should have a K much less than 0. Let's talk points really quick. You get 1 point for writing the K expression right here. You get 1 point for finding each of these values. If you found these values and just wrote them here, or stated them implicitly via math anywhere, you'd also get the point there. And you get 1 point for successfully calculating your KP. There you go. On to C. C continues on and says, nitrogen monoxide or NO gas can undergo further reactions to produce acids such as HNO2 or nitrous acid, a weak acid with a Ka of 4.10 times 10 to the negative fourth and a pKa of 3.40. The student is asked to make a buffer with a pH of 3.40 using 0.10 molar nitrous acid and 0.1 molar sodium hydroxide. Neither of these problems will be on the 2020 AP exam, which is why they're starred, but they are material we have covered, so you should be able to do them at this point. Explain why the addition of 0.100 molar sodium hydroxide aqueous to 0.100 molar nitrous acid can result in the formation of a buffer solution. Include the net ionic equation for the reaction that occurs when the student adds NaOH to the HNO2. So it tells us what it wants right here. Include the net ionic equation. Why don't we start there? So I'm going to add sodium hydroxide plus nitrous acid. And whenever I add an acid and a base, I'm going to get water. And in this case, sodium nitrite. Okay, so the net ionic equation has all the spectator ions, all the ions that sit around to do nothing, thrown out. So what we need to do here is take our formula equation, break it down to our complete ionic, where we have everything just split up. Sodium hydroxide is a strong base, so it'll split up to sodium and hydroxide. Nitrous acid is a weak acid. How do I know it's weak acid? It's not one of the 7 strong acids. And it also literally says it is a weak acid right there. So it stays together. Water is a liquid. It will also stay together. And the sodium nitrite will split up. And the only thing that we see on both sides, the only ion that shows up on both sides is the sodium. So that's the only thing that gets canceled out, leaving me with a net ionic equation of hydroxide plus nitrous acid goes to water and nitrite. And the entire story kind of comes out of that equation. Here we have the addition of sodium hydroxide to nitrous acid. In adding the sodium hydroxide, it produces nitrite, or the conjugate base of nitrous acid. And then we have a solution with both nitrite and nitrous acid, which would give us a buffer solution. And there we go. We explain why adding NaOH to the HNO2 gives us a buffer solution. And it comes down to the net ionic equation. A more proper way of saying this, according to the AP exam, would be sodium hydroxide will neutralize some of the nitrous acid to produce nitrite, The resulting solution contains a mixture of the weak acid and its conjugate base, which is a buffer solution. You get 1 point for the correct anionic equation. And you get 1 point for your explanation, which you explicitly need to include the fact that their solution is a mixture of a weak acid and its conjugate base. Part 2, which is also not in the 2020 AP exam, says determine the volume in milliliters of 0.100 molar sodium hydroxide the student would need to add to 100 milliliters of 0.1 molar nitrous acid to make a buffer with a pH of 3.4. Justify your answer. And this one looks a little tricky, a little hard. Looks like it requires a lot of math, but it ultimately doesn't. There's a really easy thing here. It tells you that they want to buffer with 3.40, but the pKa up here is also 3.40. And what this tells us is that the concentration of nitrite has to equal the concentration of nitrous acid, or you need the same number of moles. And if you don't believe me, we can go back to this equation, which is pH equals pKa plus log A minus over HA. Okay, the Henderson-Hasselbalch equation. And we want 3.4 for our pH, but our pKa is 3.4 plus log A minus HA, which means that our concentration, the only way this equation works or will be true is if this is 0. Or in other words, if log A minus over HA equals 0. And that only happens when A minus over HA equals 1, or when A minus equals HA. Okay? Which means we need to get rid, or convert more accurately, half of the HNO2 into NO2 minus. Half of the 100 milliliters is 50 milliliters. So we would need to add 50 milliliters of NaOH to the solution to neutralize it. Let's go a little more in depth. The student should add 50 milliliters of 0.1 molar NaOH. Why? Because that will neutralize exactly half of the nitrous acid. How do we know that? Because they're both the same molarity, 0.1 and 0.1. So half of the NaOH will neutralize half of the nitrous acid. Okay. When half of the HNO2 is converted to the conjugate base, the concentration of HNO2 will equal to your concentration of NO2 minus. Therefore, the buffer will have a pH equal to pKa, or go back to Henderson-Hasselbalch and go, okay, well, if this is going on, your pH will equal your pKa when these two are equal. You don't need to do a calculation, you just need to explain, and you need to indicate that there's a 1-to-1 ratio of your weak acid and your conjugate base. This was worth 2 points. 1 point for your indication of the correct volume, and 1 point for the relation that these should be a 1-to-1 ratio. Okay, taking us to 7 points earned total on this problem already. On to D. D asks, a student makes a buffer by dissolving 0.1 molar of sodium nitrite solid in 100 milliliter of 1 molar nitrous acid. Which student is more resistant to changes in pH when a strong acid or base is acid? The buffer made by the second student or the buffer made by the student made in the first part, C? So which buffer is better at resisting changes, or which buffer has a higher capacity? Well, if we think back or remember, buffer capacity is based on two things. The first is the concentration, and the second is how close that buffer is to the pKa value. In this case, we're told that the buffer, we're not told anything about how close the buffer is to the pKa value, though in C we explicitly say it's at 3.4. We don't have that information in D, so we can't make a comparison there. What we can say, however, is that there is a larger concentration of HNO2 and NO2 minus in the second solution made by the student in D than there is in C. We can say this for two reasons. The first is right here, it says 1 molar. In the previous problem, we were using 0.1 molar. So right off the bat, we have more NO2 per milliliter of solution, or a higher concentration. We have more NO2, which means it'll be more resistant to change. The second is we're adding sodium nitrite as opposed to removing nitrous acid by adding a base. Both of these will increase the overall concentration of the buffer components, which will make it more resistant. There are many different ways to say this or justify it, but ultimately the student in D will have a better buffer, or the buffer made by the student in D will be more resistant to pH changes from an addition of a strong acid or a strong base because it has a higher concentration. Justify that how you will, talking about the lack of decrease, or talk about how this is 0.1 molar off the bat. Either way will work. E continues on and says a new buffer is made by using nitrous acid as one of the ingredients. A particular representation of a small representative portion of the buffer is shown below. Cations and water molecules are not shown. Is the pH of the buffer greater than, less than, or equal to 3.4? Justify your answer. And this, once again, seems like a lot, but isn't that bad. This goes back to Henderson-Hasselbalch. What we need to know is if we have more NO2 minus, more HNO2, or the same amount. If we have more NO2 minus, going back to Henderson-Hasselbalch will tell us that if there's more NO2, we will have a pH greater than 3.4. If we have more HNO2, we'll have a pH less than 3.4. And if we have equal amounts, the pH will be equal to 3.4. And this goes back to, once again, that equation and the concentration. So first things first, let's count how many of them we have. NO2 are these gray dots without the circles on them or without the hydrogens on them. We have 1, 2, 3, 4, 5 of those. Whereas HNO2, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have twice as many HNO2 than we have NO2. So when we go to the Henderson-Hasselbalch equation, which, let's scroll to that really quick. Here we are, back up at our equation sheet, which says pH equals pKa plus log A minus over HA. Even if we don't know the exact volume, we can get a rough number. It's 5 over 10, or log of 1/2. Log of 1/2 is negative 0.3, so our pH will be less than 3.4. We can do it with the math that way, justification. The scoring guidelines even have that in there, or alternatively, we could just talk it out. The pH of the solution is less than 3.4. That's worth 1 point. The second point would be justification either with the math or description, such as if the concentration of the acid and the nitrite were equal, pKa will equal pH. If the pH of the solution, and this pH of the solution would be 3.4. Since the concentration of the HNO2 is greater than the concentration of the NO2 minus, as represented by the diagram, the solution has a pH less than 3.4. Either way, however you want to handle that, that's done. You get 1 point for justification, 1 point for your answer, for a total of 10 points on the problem. And that's 2017 AP Chemistry FRQ number 3.